Welcome to the next video on compiler design. In this video, we are going to talk about shift reduce parsing. But before that, let us look what exactly a parser is. A parser for grammar G is a program which takes as input a string W and produces as output either a parse tree for the W if W is belonging to the language generated by the grammar G, that is sentence of G, or an error message indicating that W is not a sentence of G. Okay, so there are two types of parser for context free grammars, that is CFG. One is bottom up parser and another one is top down parser. As the name suggests, it starts with the root and builds the parse tree, goes to leaves. Fine. Top down parser work like this. While just reverse happens in the case of bottom up parser. Starts with the leaves and goes up to the top, that is the root of the tree. Okay. Now the bottom up parsing is called shift reduce parsing. Why? Because it consists of shifting input symbols onto the stack until the right side of the production appears on the top of the stack. The right side may then be replaced by or reduced to the symbol on the left side of the production, and the process is repeated. For example, suppose S is rewritten as A This right side, if it appears on the top of the stack, then this can be reduced by left hand symbol, that is S. Okay. Now coming on to the some important facts and points. The sequence of productions used in some derivation is an example of an implicit representation. Fine. A linked list structure for the parse tree is called an explicit representation. So, if alpha derives beta by a leftmost derivation, we write alpha is deriving beta in 0 or more steps and writing lm under this. Okay. What exactly a leftmost derivation means or rightmost derivation means, you can watch the previous videos. The link of these videos will be in the description only. Okay. If S derives alpha in 0 or more steps in leftmost derivation fashion, then we say that alpha is a left sentential form of the grammar at hand. Okay. In a similar way, rightmost derivation is being represented. Alpha is deriving beta in 0 or more step. Rm is used for representing the rightmost derivation. Similarly, right sentential form, if start symbol derives alpha in 0 or more step in rightmost derivation fashion, then it is called as right sentential form. Also, rightmost derivations are called canonical derivations. Okay. Now consider this grammar. G is equal to VTPS. Here the non-terminal set consists of S, C. Okay. The terminal set I, T, E, A and B. These are the production rules, and S is the start variable or non-terminal. Okay. Now suppose if a string W is given like I, B, T, I, B, T, A, E, A, and we have to find whether this W belongs to language generated by this grammar G or not. So what we can do? From start variable, we try to derive this string. Here you can see S is rewritten as ICTS by using production 1. Fine. Next, by using production 4, C is replaced by B. Again, S is rewritten as ICTSES by using production number 2. C is rewritten as B, S is rewritten as A, and S is rewritten as A. If we read from leftmost leaf to the rightmost, then we are going to get yield of this parse tree or derivation tree. Fine. So what exactly is the yield? I B T I B T A E A, and which is nothing but the W itself. So we can say that this W has been derived from the start variable. So this belongs to the language generated by the grammar G. It can be shown in this manner also. S derives ICTS in leftmost derivation fashion by using the production 1. Again IBTS by using production this 4, and so on, ultimately reaching to W. Okay, so S is deriving W in leftmost derivation. Fine. A leftmost or rightmost derivation is equivalent to a past tree. We have seen that. Now coming on to the shift reduce parsing. It is an example of what? Bottom up parsing. We can think of this process as one of the reducing a string W to the start symbol of a grammar from leaf to root. At each step, a string matching the right side of a production is replaced by the symbol on the left hand side of the production rule. Now consider this grammar. Here you can see variable set consists of S, A, B. The terminal set is what? A, B, C, D, and E. These are the production rules, and S is the start symbol. Now suppose we have this string A, B, B, C, D, E. Now we will try to reduce this string to the start symbol or start variable. Okay. So we want to reduce this string to S. Now suppose if we choose the leftmost B and replace it by A. What was the string? A, B, B, C, D, E. Leftmost B at position 2. Okay. So A, B, C, D, E, as we have replaced B by the LHS of the production rule. Now in the same manner, this AB, we have the production rule. A is rewritten as AB. So this AB has been replaced by A, getting A, C, D, E. Again, this D is replaced by B, as we have this production. B is rewritten as D. So A, C, B, E. And you can see the first production. S is rewritten as A, C, B, E. So this can be now replaced by start variable. Okay, so ultimately what happened? We have reduced w to start variable. So each replacement of the right side of a production by the left side in the process above is called what? A reduction. Okay. Now coming on to the next important fact, handles. Okay. A handle of a right sentential form gamma is a production. A is rewritten as beta and a position of gamma. So we have one right sentential form gamma in which we are defining handle. So a production A is rewritten as beta and the position of gamma where string beta may be found and replaced by A to produce the previous right sentential form. It is very much of importance that we are going to produce previous right sentential form in a rightmost derivation of gamma. Suppose S is deriving in rightmost derivation fashion. At one step we are having alpha AW and in the next step we are having alpha beta W. Then this beta is going to be replaced by A and this position is what is called handle. A is rewritten as beta in the position following alpha in this string is handle of alpha beta wy because we are getting previous right sentential form. Okay, now the string w to the right of the handle contains only terminal symbol. This is again one important observation. Okay, now the example that we have discussed earlier, consider that only a b b c d e, it is a right sentential form. Now 1 2 3 4 5 and 6, a is rewritten as b at position 2. Fine, it is handle for this string. Again a is rewritten as ab 1 2 3 4 5 6. This is handle for this string at position 2. Fine. If a grammar is unambiguous, then every right sentential form of the grammar has exactly one handle. Consider the grammar. E is rewritten as E plus E. E is rewritten as E multiplied by E. E is rewritten as in parenthesis E and E is rewritten as ID. Okay. Now we have this string at hand, ID1 plus ID2 into ID3, and we are going to derive it in rightmost derivation. So E is rewritten as E plus E. We have used this production 1. Fine. You can see the rightmost variable is E and this is being replaced by E into E. Next, we are having this as the rightmost variable ID. E is rewritten as ID. So this ID3 again in the next step, this is the rightmost variable ID2 and only one variable is left, so ID1. If we traverse in this manner from string to the start variable, then what happens? ID1 is a handle. Fine, because ID is the right side of the production, E is rewritten as ID. Okay, and replacing this ID1 by E, we are going to get the previous right sentential form. Just consider this, E plus ID2 into ID3. In the same way, ID2 is going to be next handle because replacing this by e, we are going to get the previous rightmost derivation, e plus e into id3. And in the same way, we can move to the start of the derivation. Okay, and you can consider the string appearing to the right of a handle contains only terminal symbols. Just see, combination of terminal symbols. Next, terminal symbols. Fine. Now coming on to this process, handle pruning. A rightmost derivation in reverse, often called a canonical reduction sequence, is obtained by this process that is known as handle pruning. Suppose we represent the rightmost derivation in this fashion. Starting with the start variable, we reach at the string or sentence of the language. S is represented by gamma 0 and W is represented by gamma n. Okay. From gamma 0 to gamma 1 in rightmost derivation, rightmost derivation, rightmost derivation, and here also in rightmost derivation. Fine. To reconstruct this derivation in reverse order, we locate the handle beta n in gamma n. Fine. And replace beta n by the left side of some production. A n is rewritten as beta n to obtain the n minus 1th right sentential form gamma n minus 1, and this process is repeated until we reach at the start variable. Okay. So if by continuing this process we produce a right sentential form consisting only of a start symbol s, then we halt and announce successful completion of parsing. Just consider the grammar of the previous example and the string. Okay. So a right sentential form, W was what? ID1 plus ID2 into ID3. Handle we have located ID1, reducing production, E is rewritten as ID. So previous right sentential form E plus ID2 into ID3. Again handle is ID2. Previous right sentential form E plus E into ID3. Next handle ID3. ID3 is replaced by E. Next handle E into E. Production was what? E is rewritten as E into E. So we are getting E plus E, and finally this E plus E is being replaced by E. So from W we are going to get the start variable. How to implement this shift reduce parsing by using an stack? So a convenient way to implement a shift reduce parser is to use a stack and an input buffer. We shall use dollar to mark the bottom of the stack and the right end of the input. So initially the content of stack is what? Dollar, and input is concatenated appended by this dollar symbol. The parser operates by shifting zero or more input symbols onto the stack until a handle beta is on the top of the stack. Okay. Then what happens? The parser then reduces beta to the left side of the appropriate production. The parser repeats this cycle until it has detected an error or until the stack contains the start symbol and the input is empty. So ultimately in the bottom up parser, what we are doing? We are starting from the leaves and reaching at the root, that is the start of the grammar, start variable of the grammar. So stack configuration at the end should be $s and the input should be only dollar because we have exhausted W. In this configuration, the parser halts and announces successful completion of parsing. Okay, just consider the example that we have discussed earlier. Initially, stack contains dollar. Input is what? W concatenated with dollar. What action is done? Shifting. ID1 is shifted to the stack. Fine. Next input becomes plus ID2 into ID3 dollar. Reduced by this production. So we are getting dollar E plus ID2 into ID3 again shift. So plus has been shifted to the stack. ID2 into ID3 input followed by dollar again shift ID2, then reduced E is rewritten in ID. So this portion ID2 is being replaced by E. Again shifting is done. Again shifting is done. Reduction is done. So we are getting E plus E into E. Again reduction is done. Reduced by E is rewritten as E multiplied by E. So this is reduced to E. Again reduction. E is rewritten as E plus E. So we are getting this configuration $E input string has already been exhausted. So in this way we are going to accept. Fine. So what are the four possible actions a shift reduce parser can make? Number one is shift. The next input symbol is shifted to the top of the stack. Reduce. The parser knows the right end of the handle is at the top of the stack. It must then locate the left end of the handle within the stack and decide with what non-terminal to replace the handle. As we have seen, suppose at the top of the stack this was present. So E was present at the top of the stack. So this makes the right end of the handle. We have located the left end of the handle and this was replaced by the LHS of the production rule, that is E. Okay. Next is accept. The parser announces successful completion of parsing. And last but not the least is the error. The parser discovers that a syntax error has occurred and calls an error recovery routine. Fine. Now how to construct a parse tree for a bottom up parsing or shift reduce parsers. So what exactly is the process? It has two aspects. When we shift an input symbol onto a stack, that is we are shifting A onto the stack, we create a one node tree labeled A. Both the root and the yield of this tree are A, and the yield truly represents the string of terminals reduced by zero reduction to the symbol A. Next, when we reduce suppose x1 x2 till xn to a, we create a new node labeled a and its children from left to right are the roots of the tree for x1 x2 till xn. So suppose this is happening x1 x2 till xn, we are reducing this to a, then what happens? This kind of tree structure comes in the picture. If we reduce epsilon to a, we create a node labeled a with one child labeled e, epsilon, like this. Okay. Considering the previous example, just see ID1 is shifted onto the stack. We have created a node. Next, reduction. E is rewritten as ID1. So E and ID1 after reducing ID1 to E. Okay. E plus E, E plus E is deriving ID1, again E multiplied by E, ID2, ID3. So in this manner, from bottom up approach, we are reducing this to this form. Okay, again this e plus e is going to be replaced by this e. Okay, reduced. So in this manner we can build the parse tree. Fine. Okay, like this: e, e plus e, e multiplied by e. These are the references. Thank you for watching.